This is for the forces of transport section of your P3 revision map. And there are really kind of two key areas, okay, within this particular part of the unit. And the first one is speed, and the second part is distance time graphs. Okay, so we'll look at both areas together. In the case of speed, when you look at speed at key stage 3, is equal to distance divided by time. And that's absolutely fine, okay, you can use that equation, but it does have its limitations. In the case of speed, when we look at speed, we're usually, if we're using scientific units, talking about speed in meters per second, where the distance is in meters and the time is in seconds. So distance over time, meters over seconds or meters per second. However, they can give you other units. So they might, for example, give you distance in kilometers. Okay, and each kilometre is equal to 1,000 metres. So in that particular case, if they give you kilometres instead of metres, and you need to convert it to metres per second because they specify that, what you have got to do is you've got to convert. Now, when you go from kilometres to metres, you multiply by 1,000. And when you go from metres into technically a smaller number, although the unit is larger, you will divide by 1,000. Another possible unit swap you might have to do is time. Time may be given to you in minutes instead of in seconds. 1 minute is equal to 60 seconds. So if you want to go from minutes to seconds, you have to multiply by 60. And if you want to go from seconds to minutes, you have to divide by 60. Okay, so there might be opportunities and times where you have to look at potentially changing your units a little bit. So when it comes to speed increasing is all about how, if you were travelling a particular amount of time and you went faster, you would travel a further distance. If, for example, you increase the speed and you want to travel a particular distance, if you go faster, you're obviously going to take less time. So these three things are very much linked together. The equation can also be improved a little bit. If we rearrange this, okay, by using our triangles, okay, what we can actually say is that the average speed, which is equal to distance over time, there's our division line here. So whatever's above the division line has to go at the top. So our distance will go at the top in meters, which leaves our average speed and our time taken to go at the bottom. Okay. If we rearrange that to equal distance, what we get is distance, cover it up, is the average speed, which is in meters per second, multiplied by the time, which is in seconds. Now, when we do practicals and you work out averages, for example, in maths, you will generally add at least two numbers together and then divide by how many numbers you've added. Okay, so for example, if I wanted to work out the average of 5 and 7, I would add those two values together, give me an answer, and then I would divide that answer by 2, which would give me 6. So when we see another equation at the front of your booklet, okay, when you're looking at your exam paper, you will also see this equation. Okay, and this is for examples where you are maybe given two speeds, a starting speed and like an end speed. And that's because what they want you to do is work out the average speed. So to work out the average speed, you add, and I'm going to write it exactly how you have it in your booklet, u plus v divided by 2. Starting speed plus the end speed divided by 2. It's no different to how you calculate the average of any two numbers. In this case, you're taking the average of the start and the end speeds, dividing by 2 to work out the average speed. That is then multiplied still by the time in seconds. But that little equation is just how you'd work out the average if you're given a start speed and an end speed. You just calculate it by working out the average of those two values. Add them together, divide by 2. So calculating speed, we can rearrange the equation. You might need to convert units. But one thing that obviously comes up is distance time graphs. And again, they are no different to the type of distance time graphs you will get in maths. Distance could be in meters or kilometers. Time could be in seconds or minutes. You will have to make sure that you convert units depending, on what you're looking at. Let's just make it nice and easy for this example and say that the distance is in meters and the time is in seconds. So in this particular case, we can work out things like the speed, for example, because we can work out the distance over time to give us the answer in meters per second. We'll have a look at that in a second. So when we look at lines on a distance time graph, means something very, very different to speed time, graphs, which is really, really important to understand. We're looking at how the distance changed from a starting point, and that starting point is 0 meters, over a period of time. So you might see graphs, for example, that go like this. Straight lines are nice and easy to deal with. That basically shows the fact that the distance, when you change that distance over time, it is a uniform change, when you have a straight line. In other words, the actual speed is constant. So you might go, for example, 5 meters per second, and then a further 5 meters for the next second, then another 5 meters for the next second. So this would be moving away from our starting point as the distance is getting further. But it would also indicate the fact that the speed would be constant during that period of time. And we can calculate that, as I'll show you in a couple of seconds. When you have a flat line in the case of a distance time graph, you're basically saying that at this distance, that's in line with that flat part, for this time change from here to here, the distance hasn't changed. So in that case, we're talking about something that has stopped moving. It's completely stationary. It's not moving at all. And when we look at a line that comes then back down to the original point where we started from 0 meters, what we'll be doing is we're moving back to where we actually started. And again, because it's a straight line, we're moving back at a constant speed. So you could be asked to calculate the actual speed for a particular part of the journey. Now, obviously, with a flat line, it's not moving, so the speed is always going to be 0 meters per second. But what you could be asked is for example, the return part of the journey, the moving back, what was the actual average speed? So when you do this, draw your line from the point where it starts to drop down to our timeline. Let's just say that happens to be 10 seconds. And the part where it's returned back to 0 meters, make sure you know what that value is. Let's just say it's 15. And then the line where it started, where originally it wasn't moving until it returned, find out how many meters that actually was. So work your way right across to work out the number of meters, and let's just say it was 10 meters. Now remember, speed is equal to distance divided by time. So the distance the object started at was 10 meters. And that to go 10 meters, took the difference between 10 and 15 seconds, which is 5 seconds. So in that case, the speed would be 10 divided by 5, which is 2 meters per second. Now, straight lines show that you have a uniform speed. The speed isn't changing, it's a constant speed. But what happens on a graph, especially on higher tier paper, where you might get something like this, so distance divided by time, and you might get a line that goes up like that. What that's showing is that the change in distance as time progresses is changing. So it's not constant, it's not the same amount of distance covered every second. Okay, it's altering. When it goes upwards, so it slopes up, that tells you that you have acceleration occurring. Okay, acceleration being an increase in speed. If you have the opposite, for example, where you have a line like this and it curves downwards, that would be talking about deceleration. Okay, so again, distance time graph, curved line, deceleration. If you're asked to work out things like the speed from the graph, then pretty much you will be looking at straight lines. They won't ask you to work out if you've got a decelerating or an accelerating line. Okay, remember, decelerating is basically slowing down. So distance time graphs could also ask you to compare. Okay, so let's say we're talking about this being a specific constant speed as we're moving away from the object. What if another object moved like this? Did exactly the same thing, moved exactly the same distance. Okay, now if you compare the time it took, you can see that it took less time to move that distance compared to this object here. So when you have a line that is steeper on a distance time graph, you're basically talking about the fact that the speed is a higher constant speed. And that kind of makes sense. You're covering the same distance but in a shorter period of time, so the speed must be more.